Hello and welcome to this module 10 of design practice 2. We were actually trying to plot a surface through various schematics, either by ruled surfaces or tabulated cylinder approach for regular solids, or surface patches with an additional degree of freedom and explicit implicit equations therein which were involved to plot such surfaces for synthetic surfaces or complex surfaces. So, just as we sort of recall the implicit and explicit way of representing the surface with an additional degree of variable, that is addition of a y variable. Okay, so, you have different combinations on x and y's resulting in some particular value of z, which would a combination of all these three would then be descriptive of an array which would be the surface itself. I am going to first outlay the parametric form of representation. Obviously, because there are two variables in this case, they are going to be a two parameter situation, where each variable, just as in the earlier case in the 2D curve case, the variable x was represented through a parameter t varying between 0 and 1, so that you could go from a global to a local level. Okay, in this particular case, because there are two different variables, you will have to have two different parameters s and t, each of them varying between two limits. So, that with the combination of all these different parameters, you should be able to again locally estimate a surface given the overall two dimensional nature of the surface which is exists, the global nature of the surface which exists. So, if we looked at how this parametric form can be represented of a surface, we are talking about an array of points V represented by two parameter system s and t, where s varies between some maximum minimum value, and similarly t varies between again some maximum and minimum value, and each of these x, y and z's, all the three coordinates, are made a function of the parameters s and t. Okay. So, x is a function of s and t, similarly y again is a function of s and t, and so is z, because z obviously depends on x and y. So, if x and y are explicitly functions of s and t, two variables, obviously z is also going to be a function of s and t. So, we will try to now plot a bicubic Hermitian surface, which is normally defined in patches, and each patch would correspond to a rectangular domain in the S-T space, just as we discussed the S domain in the previous section. And then there is a question of connectivity of these patches, so that the whole surface is described by patches getting connected to each other. It's just a little different in terms of operability, because in the 2D planar case we are talking about joining curves. In this case we are talking about joining the patches. So, obviously, the patches would extend both in the s direction as well as the t direction, okay, so to describe the whole surface. So, it is slightly more complicated than just joining segments. And just as there is a characteristic third order equation to describe two dimensional curves, there is a third order 16 term series to describe the cubic parameter equation for a surface, which I am going to outlay before you now. So, we are talking about let us say an array of points are described by V, which is a function of two parameters s and t, represented in a manner like sigma I varying between 1 to 4, again j varying between 1 to 4, a I j s to the power of I, t to the power of j. So, the ease of convenience is taken care here, because we want to talk about parameters in terms of a for I equal to 1, j equal to 1, 1, 2, 1, 3, so on and so forth on one hand, and then we also want to use parameters starting from s to the power 0 or t to the power 0 and all the way to the total number of n minus 1. So, just as it was a 4 term series with t to the power 0, t to the power 1, 2 and t to the power 3, it is a cubic polynomial, you remember. In this case also, although there are 4 different indices which are there, we just wanted to make sure that we have a two different cubic polynomials estimating both the parameters, which would eventually result in sort of a 16 term series, okay, describing the two dimensional curve. So, we are just trying to represent V in that manner. If I expand this term, we would have something which looks like what the Hermitian cubic fit was in case of a planar curve, namely a11 plus a12 t plus a13 t square plus a14 t cube times of s to the power of 0, okay, plus again a21 plus a22 t plus a23 t square plus a24 t cube times of s to the power of 1, okay, plus again a31 plus a32 t plus a33 t square plus a34 t cube times of s to the power of 2 or a square, plus again a41 a42 t, let me write this little properly, plus a43 t square plus a44 t cube times of s to the power of 3, where t varies between 0 and 1 and so does s varying between 0 and 1. So, if we wanted to represent this in terms of a more simpler matrix multiplication equation, we can conveniently represent it as VST equals a multiplication between the S matrix, the A matrix, and the transpose of the T matrix. So, I will just write it down as 1 t t square t cube, something like this. So, that is what this 16 term series could be represented as, where you can find out the parameters independently coming out, and aij being the unknown variable which we need to find out through just as we did in the previous case, considering both the end points as well as end slopes. In this particular case, it is a 3-dimensional surface that we are talking about. So, obviously, both the s and t's would vary between 0 and 1, and so there is going to be a slope with respect to the s and the slope with respect to the t at all the 4 corners, because obviously, as a planar curve would hinge to 2 points, the beginning and the end points, a surface would hinge to 4 points, which is like a sort of a rectangular or square surface corresponding to S0 T0, S0 T1, S1 T1, and then again S1 T0. So, you will have 4 different end conditions this way, 4 slopes, okay, and so slopes at these 4 points along both the directions, and there are cross slopes. So, what I am going to do is to sort of try to write the just as we solved for the Hermitian planar curve example, where we independently put the values of V0, V1, V dash 0 and V dash 1 to calculate the variables which were the A0, A1, A2, A3 values. In this particular case also, if we do that computation, we would be able to transform or produce a transformed set of equations through various things which are going to be formulating. So, it basically consists of the S matrix, it contains the T matrix, it also contains sort of a slope matrix, slope and point matrix, which is concerned with all the 4 corners across which this patch is hinged, corresponding to the different values of S's, S equal to 0, T equal to 0, to S equal to 1, T equal to 1, all the combinations therein which exist at all the 4 corners. And then there should be some kind of a basis matrix which gives you a coefficient value or a set of coefficients which would then match the whole equation. This is exactly the same approach as we used for a 2-dimensional case to plot a curve that we are doing on a surface. So, in this particular case, while doing the transformation on a parametric cubic curve, we just as we generated a basis matrix M which we applied to transform the old basis function to the new basis function. Same manner for the surface, this transformation may be written down as V S T equals U m A m transpose V transpose, where the M is basically what we know as the basis matrix. Remember, this was matrix full of coefficients. Okay. So, in this particular case, the M is given as a 4 by 4 matrix, namely 1 0 0 0 0 0 1 0 minus 3 3 minus 2 minus 1 and 2 minus 2 1 1. Okay. The S matrix and the T matrix are already mentioned in the last step here, and we have a matrix further, okay, which is a 4 by 4 matrix of the vector as in the next page. Let us plot that A by 4 by 4 matrix. A in this case is defined as a set of points, which is V 0 0 corresponding to V 0 1, V 1 0, and these are all values of S at different points or different corners of the rectangle, for which we are defining the patch. So, you can call them as hinge points of the particular patch. Then because it is a 4 by 4 matrix and we have 16 terms, so we should have a slope in the t direction. Okay. So, V t 0 0, V t 0 1 again, V t 1 0, V t 1 1. Okay. There should be the slopes across the s direction of, or at all these hinge points, V s 1 0, V s 1 1. Okay. And then there should be the cross slopes, which means V s of t 0 0, V s of t 0 1, V s of t 1 0, V s of t 1 1, so on and so forth. So, that is how the A matrix is defined. Okay. So, when we are talking about these set of terms here, that is V t 0 0, V t 0 1, V t 1 0 and V t 1 1, we are talking about del by del t of the V function in S and T, okay, evaluated at the different values of S and T as given in this. When we are talking about the same V s 0 0, V s 0 1, V s 1 0 and V s 1 1, we refer to the slope in the s direction or with respect to the s parameter. And then when we are referring to the V s t 0 0, V s t 0 1, V s t 1 0 and V s t 1 1, we are referring to the cross slopes, that is del 2 by del s del t or del t del s, whatever it is, of V s t, evaluated again at the different values of the s's and the t's. So, at the four corners we are referring to the slope along the physically along the direction of the parameter t or the direction of the s parameter, and then we are pulling out a function where we are talking about initially a derivative along the t, then along the s direction, or vice versa. It is all the same, whether it is del 2 by del s del t or del 2 by del t del s is going to be the same as per the conventional partial derivatives, scheme of partial derivatives. So, this is how the data structure would then be created for a surface, because now if we send in the various values of the s's and t's in terms of fractions. For example, remember when we were plotting the Hermitian curve, we talked about the various values of t starting between starting from 0, 1/4, half, 3/4, 1, so on and so forth. So we do the same for t and same for s, and so there is at least 25 different combinations of these values across which you could find out an array of points. And if I plotted this array of points on a 3D space, that is what we are recording the surface patch as. And remember that if there are such patches in series with each other, that would help us to describe the surface in totality. So let us actually look at a problem little more carefully, so we can actually try to plot such a surface. So let us say the problem is about the 4 corners of a surface which are to be plotted, and these points are A 0 0 1, B 0 2 2, C 4 0 0, and D 4 2 3. So these are the definitions of the points V at the first place. Remember in the Hermitian curve case, we had a first point and the last point of the curve. So in this case there are 4 points of a surface. So assume for first iteration to generate the surface that the slope with respect to s and t at ABCD are unity and the cross slopes are 0. So we are trying to simplify the computation through this. So we will try to plot or develop a Hermitian patch. So we want to solve this equation, and for this what I would suggest is that rather than manually solving, because this problem becomes extensive, some of you may have access to a package like MATLAB which you could use for solving. So this whole transformation equation can be written down as U m a m transpose v transpose, which in this particular case we are going to again represent as 1 s s square s cube times of the basis matrix which is again a 4 by 4 matrix. In this particular case we are talking about 1 0 0 0 0 0 1 0 minus 3 3 minus 2 minus 1 2 minus 2 1 and 1 times of the A matrix. In this particular case the A matrix has a set of 3 points, let us say 3 coordinates x and y and z for the different points, the hinge points of the particular surface. So let us say A at 0 0 1 or B at 0 2 2 or C at 4 0 4, D at 4 2 3, and further we know that the slopes in the S and T directions for all the 4 points are unity, and the cross slopes are all 0. Okay, so that is how we have formulated the A matrix times the M transpose, which in this particular case would be 1 0 0 0. Here let us say we call it 0 minus 3 2, and similarly you have 3 minus 2 1 0 here, and then finally again minus 2 minus 1 plus 1 and 1 times of 1 t t square t cube. So for the various values of s and t, let us say supposing we have the values of s equal to 0 1/4, half, 3/4 and 1, and similarly t equal to 0 1/4, half, 3/4 and 1. So we should have an array of something like, with the solution for this whole problem, close to about 25 points, which would then be plotted on a surface grade in the x and the y direction, which are exactly 5 points in the s parameter side and 5 points in the t parameter side to describe a certain surface. So, I am not going to actually show you how I did this MATLAB oriented computations, but if I wanted to look at how the plot of the surface would look like, it typically looks something like this, okay, which we are considering. Here probably we took a little more than just 5 different points. You could take points in the extent of, let us say, 0.1 or 0.2 to resolve the surface very well. And so, you can see a 3-dimensional surface patch getting generated, which has variation along 2 independent variables in the s and the t direction, okay, and a certain value of the z based on whatever are these s and the t values at a certain point. So, in a nutshell, what you have observed here is that how extensively a surface can be plotted in terms of data which are just not limited to the bounds of the curves which are defining the corners or the edges of the particular surface, but you are formulating the data structure for the whole surface for every crevice or every hills and valleys which are there on that particular surface. Further, if such data structure exists, it is very convenient for us to study the intersection of such data structures and trying to then plot things geometrically when such intersections do happen. For example, if you had a plane cutting a cone or a plane cutting a cylinder, can I get a set of surface points if the plane is at varied angles. So, this is a very interesting way of finding out the exact coordinate mathematically by storing this vast data structure, okay, through which you could do computations, etc. So, I think that brings us to an end of this module on the geometric transformations and computer aided designing, which almost all designers should understand from a perspective of what goes in to one, of course, one aspect is about the how well you are or how well versed you are with the different shapes and forms, but the other a little more slightly more higher level aspect is about how you generate these in terms of coordinate maps. So, I think the module that has been covered or the few modules that have been covered in this direction make extensively this idea clear that how such data structures could be handled by a designer, and this can be very useful for people who are going to design CAD softwares, or even people who are going to be using curve fits for problems related to reverse engineering of designs, drawings, trying to then outlay their own version of the design based on what has been extracted. So, a lot of this can be done if you can go through all this process steps related to how data structures are created from different geometries. So, we have not only covered the regular kind of geometries, but also have delved quite a bit into the organic forms and also the organic shapes, okay, which can relate very well to the complex contours, etc., associated with surfaces. So, I would like to bring an end to this particular module. Probably in the next module we are going to look into another aspect of this course, which is about sensors and actuators and MEMS, which is microelectromechanical systems. So, till then, goodbye, thank you very much.